Good morning, friends. This is a setup of balancing of rotating masses. Okay. First, I would like to show you what is unbalancing. Okay. Here you can see in this video there are couple masses which are mounted on the shaft over here and which are not placed correctly. Because of that, you can see what is going to happen. So you can see how the structure is how the structure is vibrating. So because of this, the structure may get failed, it may get collapsed also. So the aim of the experiment is to balance these masses. Balancing is nothing but keeping these masses at the right places so that there will be least vibration when the shaft is rotating. Okay, so we'll see this in the conducting the experiment. Good morning, friends. I welcome you to the design lab. I am Professor Arvind Mudivya. Today we are going to engage the experiment about balancing of rotating masses. Aim of the experiment is to finding dynamic balancing of masses rotating in different planes. As you saw in the video that how the structure was vibrating because of unbalanced masses mounted on the shaft. Based on that, we are conducting this experiment for balancing of rotating masses. So how to balance that structure so that the structure remains stable while rotating of the shaft. Okay, to do that, we have to go through this observation table. So we have four masses which are attached to the shaft. Okay, the first mass is 0.184 kg it is. For that we had attached one screw that weight 0.002 kg. So totally it becomes 0.186 kg. Okay, I would like to just show you once again. We'll be having a mass like this whose weight will be 0.186 grams. 0.186 kg, and we consider this aligned screw, okay, whose weight will be 0.002 kg. So totally it becomes 0.186 kg. Similarly, we have mass of 0.170 plus 0.002, it becomes 0.172 kg. Similarly, we have a mass of 0.194 plus 0.002, it becomes 0.196. Similarly, we have 0.164 kg. So these masses we have arranged in order on the shaft, and we need to find the CG, the radius, that is a distance of CG from the center of radius. Okay, that we'll discuss now. If you look into this picture closely, okay, here we have a thread, which is wounded on the mass, okay, and we have to adjust this distance so that it can be balanced perfectly. Okay, you can see that it is balanced perfectly with the help of this thread. Now you have to measure the distance of center of rotation to the distance of CG. Okay, this distance we have to measure, which is given by symbol small r, from the CG to the center of rotation. Okay, this distance we have to measure. Here we'll be having if this is the thread what it is placed, okay, we can measure from thread to tip of this distance, and this center distance will be known to us. Okay, this slot diameter will be equal to diameter of the shaft, and its center will be the radius of the shaft plus this distance we are going to measure. Okay, so by adding these two distances we are going to get the value of r. So that is the distance between the CJ and the center of rotation. So here we have shaft radius as 12 mm plus the thread from the center from the CG to the tip of the slot is 8 mm. So it becomes 20 mm. Similarly for 0.172 kg we have shaft diameter shaft radius as 12 plus thread distance from CG to the tip of the slot, it is 6, both together 18 mm. Similarly for 0.196 kg we have 21 mm. Similarly for 0.164 kg we have 18 mm. So this is the value of R. Next we have a force. Force is a product of mass into the distance or the radius. So multiplying 0.186 with the 20 we are going to get 3.72 kg millimeter. Similarly 0.172 multiplying with 18 we get 3.096 kg millimeter. Similarly we get 4.116 kg millimeter and 2.952 kg millimeter. Right. In the experimental setup, the total length of the shaft is 220 mm. Okay, if you consider this as the one end of the shaft and this as the other end of the shaft, the total length of the shaft is 220 mm. So initially we take 50 mm this side and 50 mm this side, and we place one mass, first mass over this end. Okay, initially you take 50 mm on this side and you place the first mass on this. The first mass what we have 0.186 kg, and from here we take a distance of 40 mm and we place the second mass. The second mass value is 0.172, and we take another 40 mm, we place the third mass, that is 0.196. We take another 40 mm, we place the third mass, so it is 0.164 kg, and remaining distance will be 50. If you add all this you will get 220 mm. So masses are placed at a linear distances, at a constant distances between them. Okay, so the same is written over in the table. The first mass, that is 0.186 kg, is considered as a reference, so it is considered as a 0. The second mass is placed at a distance of 40 mm. The third mass is placed at a distance of 80 mm from the first mass, and the last mass is placed at a distance of 120 mm from the first mass. So this is how these values are written: 0, 40, 80 and 120. I will show it on the figure also. Okay, if you consider this mass as reference, so it is 0. The second mass is at a distance 40. The next mass is at a distance of 80. 40 plus 40 is 80, and next mass is at a distance of 120, that is 40 plus 40 plus 40, so it is 120. So this is how it is written: 0, 40, 80 and 120. Next we are going to calculate the couple. Couple is the product of m into r into l, that is m into r into l. These product we need to calculate. So for the first one we get 0 because the reference plane or the reference mass is considered as 0, so it is 0. Second one we get it as 123.84. Third one we get it as 324.28, and third one we get it as 359.24. Multiplying mass, radius and length, we get these values. So it is kg mm square. So after getting these values we have to draw the couple polygon. So to draw the couple polygon I will consider this as a reference I will consider this as a reference, and I will write this angle as 0 degree. I will take this mass angle as 0 degree. So I will take this as at 0 degree. The length is 123.84. You have to select a suitable scale to draw this couple polygon. Okay, so 123.84. You can take 1 centimeter is equal to 50 kg mm square also. Okay, so based on that you can draw this couple polygon. So this is 123.84. Later you have to set your compass, take the compass, set your compass to 324.28, that is next value. This as a center, draw a arc like this at a distance of 324.28. And for next value 359.24, set your compass, take this as a center point and cut the arc. So wherever you get that point of intersection of those two arcs, join these two lines. After joining these two lines, find this angle. This is angle theta 3. So according to this calculation we get 98 degree. So I will write this as 98 degree. And from this horizontal reference line you measure this angle. Okay, this is theta 4, and so this we are going to get it as 257 degrees. So now we left with what is this angle. To do that we have to draw the force polygon, okay, based on this force column. Okay, so second mass is considered as 0 degree. So I will write this 3.096 length at a angle 0. I will draw this. Next I have 4.116. So what is the angle? 98 degree. So at 98 degree I have to draw this angle. I have to draw this line. So this is 98 degree. I have to draw this. From this point I have to mark angle theta 4, which is 257 degree, So what is the length? Length is 2.952. okay, you have to draw a length of 2.952. From here you have to connect to the end of this point and you have to measure what is this angle. So this is theta 1. Okay, so you have to measure what is this angle. So theta 1, after measuring you get it as 215 degree. Now you have to set all the masses on the shaft with respect to these angles. For second mass it should be 0 degree. For third mass it should be 98 degree. For fourth mass it should be 257. And for fifth mass it should be 215 degree. When you set all the masses at these angles, the structure will be completely balanced and there will be less vibration when the shaft will be rotating. Okay, and we'll check this on the experimental setup now. Okay, we are provided with a tool. Over here we have two tools. The length of this is 50 mm and length of this is 40 mm. Okay, which is used to place the first mass and the second mass. Okay, and here you can see this, the first mass is placed at a distance of 50 mm from this end, and from this end also it is placed at a 50 mm, and distance between each mass will be 40 mm. Here you can see it will be of 40 mm. Next, the second mass, that is 0.172 kg. Okay, here you can see it is placed at an angle of 0. Here you can see on the disc, this is the pointer you can see, which is 0, and with the help of this tool I am confirming its position, and it is also showing it is a 0. Okay, it is perpendicular, that is parallel to this plane. Okay, it is 0. Similarly, we have to set up other tools. First we have to fix all the masses like this, then we have to rotate this to the required angle. Say the third mass is to be at 98 degree. By setting this pointer at 98 degree, we are fixing this. And we have to adjust this mass. Okay, now I have fixed the third mass like this. You have to check its position. Okay, these two surfaces should be in contact and this surface should be in contact. So good morning students. This is a setup of balancing of rotating masses. Okay, first I would like to show you what is unbalancing. Okay, here you can see in this video there are couple masses which are mounted on the shaft over here and which are not placed correctly. Because of that you can see what is going to happen. So you can see how the structure is vibrating. Okay, how the structure is vibrating. So because of this the structure may get failed, it may get collapsed also. So the aim of the experiment is to balance these masses. Balancing is nothing but keeping these masses at the right places so that there will be least vibration when the shaft is rotating. Okay, so we'll see this in the conducting the experiment.